Let A be an n by n matrix with complex entries, and let lambda be an eigenvalue of A. We're now going to look at two quantities associated with lambda. The first is called the algebraic multiplicity of lambda. Remember that the eigenvalues are precisely the roots of the characteristic polynomial of A, and the algebraic multiplicity of lambda is the number of times lambda appears as a root of the characteristic polynomial. For example, if my matrix A is this, then the characteristic polynomial of A is given by 1 minus lambda times 2 minus lambda squared. And so there are two distinct eigenvalues, 2 and 1. And 2 will have algebraic multiplicity 2 because it appears as a root of the characteristic polynomial 2 times. Whereas 1 will have algebraic multiplicity 1. The other quantity is called the geometric multiplicity. The geometric multiplicity is given by the dimension of the eigenspace for the eigenvalue lambda. And the eigenspace for the eigenvalue lambda will be denoted by script E subscript A, open bracket, lambda, close bracket. And we're now going to look at the definition of the eigenspace. So the eigenspace of A for lambda is given by the null space of the matrix A minus lambda times the identity matrix. And remember that the non-zero vectors in the null space of A minus lambda I are precisely the eigenvectors of A with eigenvalue lambda. So let's go back to the matrix here and see what the geometric multiplicity of the eigenvalue 2 is. So we're looking at the null space of A minus 2i, which is precisely 0, 1, 0, 0, 0, 0, and 0, 0, minus 1. And this matrix is rank 2, so the dimension of the null space of A minus 2i is 1. So what that means is the eigenvalue 2 has geometric multiplicity 1. Notice that for the eigenvalue 2, the geometric multiplicity is less than the algebraic multiplicity. And in general, the geometric multiplicity of any eigenvalue cannot exceed the algebraic multiplicity of the eigenvalue. And we have seen that in general, this inequality can be strict. Now notice that if you have an eigenvalue that has algebraic multiplicity 1, then automatically its geometric multiplicity must be 1 as well. First of all, the geometric multiplicity of the eigenvalue cannot exceed 1 in this case, but it has to be at least 1 because by definition, we must have a non-zero vector in the null space of A minus lambda I. And that means the rank of that matrix cannot be 4. So the dimension of the null space must be at least 1. We'll see later on that the geometric multiplicities of the eigenvalues can help us determine if we can diagonalize a matrix. Diagonalizing a matrix will help us compute powers of the matrix. And that's something we'll look at in more detail in a later video.